Could you see my screen?
Yep, I can see your screen.
Okay, thanks, Brian, for introduction. So I'm Haizhong, and I'm currently a postdoc at CMU working with BD. So today I'm happy here to share two of our recent work on how we can make the reinforcement learning for large language models more efficient and more stable. Uh, so, as we all know that reinforcement learning has become one of the most important components in the entire large language model training pipeline. I think since the early last year, people start to hear about the DeepSeek R1 or the OpenAI O1. So they are all kind of use the reinforcement learning to enhance the model learning abilities, so that the model can handle more complex and difficult problems. So compared to the standard pre-training or the middle training, the key difference from the reinforcement learning is that it will generate the data online rather than use a static data set. So actually, you can think about reinforcement learning in some perspective is a pure data problem. So it will use some way to generate data and find some specific training algorithm to utilize those data to optimize the model. And a good part for reinforcement learning is that it can save lots of human labeling, human annotation efforts on generating some static data sets. And on the other hand, so reinforcement learning can kind of allow the model to self-explore in some specific domain, and so that the large language model or the agents itself can find some very special solutions that even human cannot find. So, however, even though the reinforcement learning can bring us many benefits, like that we can save tons of the human annotation, and we can allow the large language model to explore some very fancy results. But the key problem for the reinforcement learning is that the reinforcement learning itself is very expensive. So, for example, this is a figure cropped from the report of Grok from the XAI. So we can see that compared to the Grok 2 and the Grok 3, Grok 4 actually use much more compute to the reinforcement learning stage, which is the orange part, and the computation is even almost same to the pre-training part. So the major reason behind that, the expensive compute of reinforcement learning is the rollout side, because in the reinforcement learning we need so it actually has two stages, the rollout and training. And in the rollout stage, we always need the large language models to generate some samples and new sequence based on the current policies or the recent policies, and then we can use those policies we can use those generated or the sampled trajectories to train the model. So here is some evaluation we run in our own cluster. So we try to train a Queen 3 base 8B model with 16 context length with a zero on the math task. And we can find that compared to the training stage, the rollout stage can be 10 times slower and expensive. So for example, for the training steps around here, so we can say that the training step kind of only use 20 seconds to complete an iteration. However, we need to use more than 2000 seconds to generate the rollouts to train this model. And this issue can even get worse for if we want to use a longer context, or if we want try to do the rollout on some more complex like the coding, and then we may need some code evaluator to evaluate the correctness of the generated code. So, and in today's talk, I'm going to introduce two parts to reduce the overhead of the rollout in the sorry in the reinforcement learning. So the first one I'm going to introduce our recent iClear paper called M2PO. So in this paper we discuss how the stale rollout data uh, will influence the reinforcement learning training stability, and how we can take advantage of those staleness to accelerate the entire reinforcement learning process. And in the second part, I'm going to introduce our newest paper, GRESO. And in this one, we are going to introduce how we can spend our compute more wisely on the rollout side, so that we can save the compute for the rollout in the reinforcement learning. So let's start with the first part, the staleness of the reinforcement learning. So, in the current open source reinforcement learning system, there are actually two popular frameworks. The first one is called the on-policy framework, so which is utilized by the I think is the most popular area framework world. And the key idea for the on-policy training is that so in each training iterations, we are going to have a batch or prompt, and then we are going to do the rollout on this batch or prompt until we complete all the trajectory collection, and then we are going to use this prompt, the batch of the prompt to do the training. So the good side for this on policy framework is that we can always use the latest policy to generate the prompt. So to generate the trajectories, so that our training can be more stable. However, one potential problem for the on-policy framework is that, so because we know that when we do the large language model generation, so there can be some long tail problems. For some examples, the generation can be very long, but for some problems, the generation can be relatively shorter. And in this case, we need to always wait for the uh, longest generation to complete, and then during this time, all other GPUs will be idle and waste tons of compute and cause many bubbles in those policy framework like Vero. So another choice to address this problem is called the off-policy framework, like Area and Slime, which becomes much more popular today. I think Vero currently also supports those like off-policy framework. So the key idea for those off-policy framework is that we are going to decouple the compute of the route and the training. So we can see in this figure, so we allocate the GPU 1 and GPU 2 for the route and use the GPU 3 alone for the training. So, and in this case, we can always fully utilize the GPUs for the rollout. And when enough examples has been completed, we are going to fetch those examples for the training. So, compared to the on-policy framework, the advantage for the off-policy framework is that it can like fully utilize all the resources and maximize the throughput for the training. However, the issue would be that because when we collect the batch for the training, there's no guarantee that this batch, all examples in this batch is generated by the current policy. So some examples can be generated by the previous policy, especially for those long horizontal tasks. So uh, So the key issue for those of policy framework is that how can we utilize those stale examples to train the model in the reinforcement learning, and we still want to keep the training stable. So in our paper, we first run a motivation study to understand how those staleness will influence the reinforcement training. So in this training setting, we use a training called the SRL training. So what we do is that so when we try to train a specific iteration, we are going to collect the trajectory from the like ACE model updates early. So for example, if we want to train a model in the 64 iteration, we are going and if S is equal to 32, and then we are going to use examples generated like in the iteration 32 to train this model. And we can see the figure here. So when we gradually increase the staleness, and we can see that the larger the S is, the larger the staleness is, and the model performance will drop as the staleness increases. So what can be the key reason behind this performance drop? Because when we increase the staleness, there are actually two factors has changed. So the first one is the data, because we are using some data generated by a very stale iteration. And those data, because the model may not be as good as the current policy, so the generated data may not be so good, which can influence the training. And second one is algorithm side, because for the current algorithm like GRPO or the PPO, so there are some trust regime will be applied on those stale data, which can influence the optimization, and this can also be a factor to influence the to cause a performance drop for the training on the stale data. So, and then we run another evaluation to try to study the true factor behind this. So, as I mentioned about that, for the current algorithm like GRPO or the PPO, so people will use the trust region to, constrain the optimization space so that the training can be more stable. So it will calculate the ratio between the behavior policy and the current policy. If those two policy or those two models diverge too much, and then it will be clipped by a range, and so that the model only use the tokens like in the trust region to update the model so that optimization can be more stable. And in this evaluation, what we do is that we totally remove the trust region. And in this case, we can kind of eliminate the cost from the algorithm side. And we say that even though without trust region, the training automatically collapse, which is as expected. But we find that it actually matches the on policy performance before its collapse. So which means that the data can kind of provide the enough information for the training. But the problem is that how we can utilize the information from those stale data and will make the training stable. And here is some additional analysis. So this is a clip ratio. So we compare the on-policy training and when the staleness is equal to over 200. And we can see that compared to the on-policy training, the clip ratio for the stale training is much larger. And if we try to study the relationship between the entropy and the importance ratio, the diverge of the importance ratio from one, and we can see that so as the ratio increases, most of those examples are kind of high entropy examples, but because we have the epsilon clipping, and then the examples in this red region will kind of be clipped out, and so that those high entropy tokens only provide very limited information to the training. So here is some the word clouds of the frequently clipped tokens with this epsilon clipping, and we can see that those commonly those frequently clipped tokens are kind of the logic connections in the sentence, like the first or let me see or let's do something. It's more like the start of some sentence or start of a component, which is very essential in the entire reasoning steps. So based on our analysis, we can uh, kind of get a conclusion on that there's actually a trade-off between the high policy data and the stable and those unstable tokens. So if we want to utilize the high policy tokens, and then the training will be like more unstable, but will be have a high potential for you to get a better model. But if you want to a more stable training, and then you will click more high entropy tokens, but the model may have inferior performance. So in this work, and then in this paper, we are trying to study how we can, exploit those high entropy tokens as much as possible while preserving the training stability. So in this paper, we propose a new optimization method for the reinforcement learning. We call the M2PO, the second momentum trust policy optimization. So compared to the traditional PPO algorithm like the GRPO or the PPO, which like you will use the importance ratio for each token to decide the clipping range. So for the M2PO, we are going to calculate the M2 value for the entire batch and then clip the examples based on this batch level constraint. And in this case, we are not go only to try to estimate the instability based on each individual examples. We are going to consider the entire batch as a one metric because for the gradient is like the calculated by the entire batch rather than for the gradient. And in this case, it will be more convenient for us to control the deviation or the variance caused by the entire batch rather than a single examples. So here is some evaluation results. So we evaluate our method with GRPO and the GSPO with the staleness or the on-policy training. So we can see that M2PO can actually achieve the comparable or even better performance compared to the original GRPO training even without any staleness. And we can also see the training curve here. So at the beginning, the M2PO have some gap to the on-policy training, but at the later stage, it will kind of match the performance for the on-policy training. And here is some clipping results for our reinforcement learning training. So we can see that so the red curve is our methods and the x-axis is clipping ratio. So we can see that compared to the GRPO algorithm, we actually clip much fewer tokens, but still keep the training stable. And the clipping ratio is kind of comparable to the on-policy GRPO training. Yeah. So I think that's the first. That's all about the first part of the our work. So we kind of study the dual nature of the high entropy tokens, and so it kind of so those high entropy tokens is very important for training. They kind of contribute to both training and instability. So the key thing is that how we can maintain a better trade-off between the how to utilize those high entropy tokens so that we can get a better performance without hurt the training stability. And then we propose the M2PO algorithm and try to maintain a better trade-off on this. And we empirically show a better performance on the still aware reinforcement learning. Yeah. So do you have any questions on this part?
So far, we didn't see any questions in the chat. That's maybe we can keep going on it.
Okay, cool.
Thanks.
Cool. And in the second part, I'm going to discuss our NUPS work on how we can spend the rollout compute more intelligent on the reinforcement learning. So when we do the reinforcement learning, there is an observation actually also in some previous work is that not all rollouts is actually informative. So for example, so this is the law sorry, this is a optimization objective for the GRPO training, and we can see that the advantage will be calculated in this optimization formula to update the model. One potential thing here is that so when we do the GRPO for a single prompt, we are going to do the rollout for the multiple example, which is named as a group. However, if all examples in this group have the same results, like they're all wrong or they're all correct, and then this value will always be zero, and then the advantage will also be zero. In this case, this example can contribute nothing to the training. So here is an statistics we collected on training Queen 2.5 Math MB model, and we can see that as a training as training process and then few examples will become effective examples. So for example, at the end or at the later stage of the training, so almost 80% of examples are kind of those zero variance examples whose advantage is always zero. And those examples cannot contribute anything to the training. So a technical proposal in DAPO to address this problem is that we can keep those out until we can fill in the batch with the informative examples, and we can filter out those zero variance examples. And we can see here, so we also run evaluation on the Queen 2.5 math data model, and we can see that after we use the dynamic sampling, we can observe a significant performance improvement compared to the vanilla GRPO algorithm. However, the cost for this technique is that because we need to keep filtering out the zero variance examples and result to get the new examples to fill the entire batch, which means that we need to roll out more examples to get the enough example for training. We can see that compared to the vanilla GRPO algorithm, the GRPO with the dynamic sampling will need to generate much more tokens or generate much more trajectories to train the model. We can see that compared to the so for example in the steps 800, the number of rollouts is kind of like 5 to 6 times compared to the vanilla GRPO algorithm. And this is actually makes the rollout much more expensive, I mean, compared to other standard training. So the key question that we want to study in this paper is that if there is a more efficient way to filter out zero variance examples, so that we can still utilize the informative examples, but we don't need to spend so much compute on the rollout side. So one analysis we do for this problem is that we try to predict the zero variance example before the rollout. So we first try to study the temporal relationship between the different prompts. We measure two probabilities. So the first probability is that so if an examples is zero variance examples in the current epoch, what can be the probability that this example was already zero variance examples in the previous epoch? And the second one is like opposite. So if one example was zero variance examples, and what can be the opportunities of these examples is a zero variance examples in the current epoch. And then we can see this figure. So we can see that especially for the orange curve, we can see that I mean after several training epochs, we can see that if one example is zero variance examples in this epoch, and then it is very likely to be a zero variance examples in the previous epoch. And in this case, one potential thing we can do is that we can use the history of examples rollout in the previous epoch to predict that if this examples is a zero variance examples for this epoch or even for the future epochs.
Oh,
So
I have a questions on the previous this one,
mhm.
like so we given the previous, so the previous here means like the previous rollout, and it's going to be a set.
Yes.
I see. And the current rollouts, it is a one single like a generation.
Yeah, actually, you can think so for the current one is more like a group of the generation. So for each prompt, we are going to do the rollout for 80 examples. And so if all 80 examples have the same outcomes, like the all correct or incorrect, and then there are zero variance examples.
I see. I
Yeah.
see. Got it. Thanks.
So what we do is that we trying to use the training dynamics for the different prompts to try to predict if these examples can be zero variance examples in the rollouts, uh, and so that we can do the filtering before the actual rollout. So we can compare the diagram of the dynamic sampling and the GRESO. So for dynamic sampling, we are going for each prompt we are going to do the rollout first, and then we are going to generate the responses for the different responses for this prompt. So if all the responses have the same outcomes, and then we are going to filter out, and then the compute on those rollouts will be wasted. However, if we do the GRESO, we are going to first collect the history for each prompt, like if this prompt is informative or not. So, for example, for some examples, if this example is always in like zero variance prompt in the previous epoch, and then we are going to use GRESO to filter it out. And also, this is not something due to a space limitation, we did not put that in the slides. So GRESO actually use a probability-based filtering, so which means that even though the example has been rejected for multiple times, it still has some possibility to be resampled and then to be explored by the GRESO again. So by this pre-rollout filtering. So what we can see is that for those rollout, we can filter them before the rollout so that we can save the computation and then accelerate the rollouts. So here is some of our evaluation results. So we can see that compared to the baseline, so the blue curve is dynamic sampling, and we can see that our method is can achieve the comparable performance with much fewer rollouts, and this can so sorry so this reduction on the rollouts can also translate to the workload time speed up, and we can so you can see the evaluation results here. So with the reduction of rollouts, we can kind of improve the improve the training efficiency 1.4 times to the 2 times. And also, even though the GRESO will filter out many examples before the rollout, but we did not see that the GRESO will hurt the convergence performance. So so this is the evaluation that we run on a larger scale model like the Queen 2.514B and the 32B. We can see that so compared to the dynamic sampling, the GRESO can achieve a comparable convergence speed with respect to the steps. And this is a more detailed analysis on how the GRESO saves the computation in each rollout stage. So we can see that if we use dynamic sampling, the effective prompt ratio will keep dropping because the model ability is getting stronger and stronger. However, if we use GRESO, we can see that the rollout can maintain a much higher ratio for the effective prompts. And also this can kind of reduce it. So if we want to get the same amount of the effective rollouts, we can see that the GRESO will spend much fewer times compared to the traditional dynamic sampling. And here is a case study on the on the rollout for the different examples. Each row is examples, and the green means that the example is selected for rollouts, and the yellow and the right means that the example is skipped for the rollout because due to it's too easy or due to it's too hard. So we can see that for those easy examples, this is kind of I mean, a case study. So the model will, I mean, so for the first epoch, the training will always sample the data for the rollouts. However, it will skip those examples, but occasionally revisit if this example is like if I mean if it can become informative again. And this is also happens for the medium examples and the hard examples. And we can see that GRESO can handle the examples with different difficulties adaptively. Yeah. So I think that's all about today's talk. So first, for the first part, we discuss about how the staleness will influence the reinforcement learning, and we see that the dual nature for the high entropy tokens. So those tokens kind of contribute to both training and instability. And the key part is that how we can design our algorithm to better balance those trade-off so that we can get as good performance for the training, and we are maintaining the training stability. So in the second part, we discuss about the how we can spend our computation of the on the rollout side so that we can reduce the computation for the rollout and without hurting the performance. Yeah, I think that's all. So do you have any questions?
Yeah. We have two questions now in the chat room, and let me share the questions here. So the first question is the difficult prompt, which is the challenging questions there might be zero variance for the
Mm-hmm.
initial model. And later they become non-zero variance because the models are learning and also they improve. How
Mm-hmm.
do your algorithm predict the transition here?
Oh, actually, this is a really good question. So this is actually something we designed in our algorithm because we know that. So for some problems, it can be too difficult for the some early stage of the models, right?
Yes,
And then when we train the model, when we keep training the model, the model have a stronger ability, and then this model can uh, probably in some later stage it can solve this problem. So what we do in the filtering side is that we are not going to uh, like permanently filter one examples. We are going to have a probability on if we are going to filter these examples in one epoch. So even though one example like is too hard for all the previous epochs, but there's still some possibility that these examples can be sampled again in the later stage for the training. And this is kind of a case study. So for example, you can see that this example is kind of skipped because it was too hard for some previous iterations, but it can still be picked in the later stage based on the probability. So does this answer your question?
I see. I also have a follow-up one. If we go back to two slides before,
Mm-hmm.
compared to the DS, the dynamic sampling one.
Do you mean this one or
Oh
this
yeah,
one?
this one. So I also wondering whether those challenging prompt they will also give the dynamic sampling many responses because we need
Mhm.
to have the non-variance reward because they are very challenging, so we need a lot of response for them.
Yeah, so actually, people usually do is not to like roll out more responses for this problem. They are going to so in dynamic sampling, people usually do is to choose some new prompts and then roll out for those new prompts. And there will always be some like a medium difficult prompt so that we can always sample the effective responses. Yeah.
I see. Thank you. And there's a second question about do we have the experiments about for other model family like Llama and Elmo? And do you see the hard example rejected in the early iterations appear as medium in the later iterations?
Mhm.
Yeah.
Yeah,
So yeah.
yeah, I think the second question is kind of same to the first question we discussed about. So for the model one, we actually do try the llama, but somehow you know that when we do reinforcement learning, the base model ability is actually very important for the training. So when we try the llama cannot benefit so much from reinforcement learning. So that's the reason that we did not report that in the paper. But we did not try the OMO. Probably that's a kind of a good choice. Yeah, to have a try.
I
Yeah.
see. Got
And
it.
for the hard example, yeah, I think that's something we discussed before. So there are actually many examples was too hard and then becomes medium in the later iterations. Yeah.
Okay, thanks. Is there any questions in the chat in a group that we want to share with Haizhong here?
I have one question. Thank you for the wonderful talk, by the way. So from what I understand, GRESO, it does use fewer rollouts, but does it use fewer tokens in the entire, for generating the rollouts? Yeah, does it use fewer tokens for generating the rollouts as well?
Could you say it again? Could you say it again? I did not fully get it.
Yeah, yeah, sure. So, if I understand this correctly, you're saying in Greece, so you're using fewer rollouts to train models,
Mhm.
but do you also use fewer tokens because you're oversampling? Like there's a trade-off, right? You're creating more rollouts. You have more tokens that are being generated, but you're
Mhm.
also not doing enough. You're not using the full rollouts, or you're not making more rollouts. So, does the number of tokens does that increase or does that decrease? Does it stay the same?
Oh, actually, we do not have a statistics on that, but we believe that so the number of generated tokens will be few because we are going we spend a kind of few the less computation on those zero variance zero variance prompt so that we can
Mm-hmm.
save the generated tokens on those prompts. Yeah. Does this answer your question? Or
I think so, maybe. I think this is just a low-level question anyways, but okay, thank you.
yeah, if it does not, just send me a follow-up and I can try to answer that. Yeah.
Sure, will do. Thank you.
Okay. Is there any other questions in the group we want to share? Okay, then thanks for Haizong his time today, and this is a really great talk, and I also learned a lot. Thanks very much. And We will have our next data seminar 2 weeks later, and that's going to be our final seminar in this semester. Thank you everyone for your attending and your time. I will see you.